Okay, if we take this region and rotate it around the x-axis, the only thing visible to us would be the outer curve. The inner curve is going to produce what, for better or for worse, we can call the hole inside the curve. If I move this thing around, you can kind of see this shape that's going inside this is the inner curve's volume that we've subtracted out. What I can do here is mess with this transparency a little bit and think of this that looks pretty solid. Think of that as empty space. That's the hole in a sense that we've bored out of this. So there is the shape that we're looking at. Here's the process of the washers filling up this volume so that we can get an idea of the shape. This black part's the little hole, and I've cut the washers in half so you can see the process. So if I sort of look in here, this has got that sort of distinctive washer shape. From the side, it's hard to see here because of the coloring, but the grayish part is the solid part, and this is empty space inside here. So at this point, Professor Mizell will take over and show you how to do this volume on paper.
All right, so this is an example of what we call washers. This is the region we're talking about here, is the graph of y equals the cube root of x and y equals x squared from 0 to 1. Again, we're still revolving around the x-axis. So here, essentially what we do is we find the volume of the top function all the way around the x-axis, and we subtract off the volume we'd get if we just did the bottom all the way around the x-axis. That's where this washer formula comes from. It's pi times the integral from a to b of essentially the top function squared minus the bottom function squared. Now, this is a very bad drawing of the region, but the question is, which is the top function, x to the 1/3, that is cube root of x, or x squared? If you're not sure, well, pick some number between 0 and 1. A convenient one would be 1/2 or 0.5, and plug it in. If you do that, you'll find that 0.5 to the 1/3 power is around 0.79, whereas 0.5 squared, well, that's just 1/2 squared, which is 1/4. That's 0.25. That is, 0.5 to the 1/3 is larger than 0.5 squared. So our top function here is cube root of x, that is x to the 1/3 power. Our bottom function here is y equals x squared. And again, it's important to get that right because the formula asked for top function squared minus bottom function squared. If this seems weird to you, remember we're only looking at numbers between 0 and 1, that is fractions. When you square a fraction, it gets smaller. So that's why 0.5 squared is smaller than 0.5 to the 1/3 power. Okay, well, once we know that, though, the rest of this is just doing the integration. So let's set it up. The volume is pi times the integral from 0 to 1 of the top function squared minus the bottom function squared dx. Make sure you square first and then subtract. It's not top minus bottom quantity squared. It's top squared minus bottom squared. I tried to emphasize that by writing it that way. So this will be pi times the integral from 0 to 1. Well, you raise a power to power, you multiply the exponent. So that's x to the 2/3. Here, that's just x to the 4th. And once again, these are easy integrals. This is pi times x to the 2/3 plus 1 divided by 2/3 plus 1 minus x to the 4 plus 1 over 4 plus 1 from 0 to 1. 1 divided by 5/3 is just 3/5, so maybe I'll write it that way. All right, so let's leave the pi out here for now. If I plug 1 in here, 1 to any power is 1. So this is 3/5 minus 1/5. If I plug 0 in, that's going to be 0, and that's going to be 0. So this is 2/5 times pi. That is, the volume of that region rotated around the x-axis is just 2 pi divided by 5.